Okay, we're gonna pick up here 15 like we were talked about last week. And that last recorded lecture, again, make sure if you have watched it, because you are responsible for the material on there. But some of the stuff that we covered in that last sort of lecture was we talked about some intermolecular forces at the end there of, or in chapter 14. Remember that intermolecular forces are, again, the forces that really hold one molecule together with another. And pretty much all intermolecular forces, as we talked about, is pretty much a basic connection between really the positive side of one molecule and the negative side of another. There's kind of three major types of intermolecular forces. There are hydrogen bonding, which can occur again when we have a polar molecule that has a hydrogen bonded to a nitrogen, oxygen, or fluorine. Directly bound to that allows it to hydrogen bond. This is really, again, the major sort of force that we find in a polar molecule that has that bond. And that is sort of how that polar molecule will interact with itself. It's also how it would interact with other molecules that have a similar type of bond as well. We have dipole-dipole interaction, which is basically how polar molecules that do not hydrogen bond basically interact with one another. And because they are polar, they always have, as we sort of talked about, a positive side and a negative side to that molecule because of the dipole moment. And again, that is where it gives it that sort of interaction to occur. Obviously, it's really the same sort of interaction happening here with our hydrogen bonding. But again, we have sort of the negative side, positive, negative side. And once again, that's going to allow those guys, again, here to hydrogen bond. The last type of interaction is really dispersion forces. And dispersion forces are pretty much how nonpolar molecules interact. Something sort of has to happen with those nonpolar molecules to create a separation of a charge so that they can do that sort of positive negative attraction. So something needs to happen to sort of turn these guys into temporary, a way that they have that separation of charge for them to sort of interact. Remember that these are the strongest interactions. This is really your weakest. And really, these type of interactions really play a really big role in kind of the first part of chapter 15 that we talked about, which is sort of solubility and how molecules are able to interact with one another or why they don't interact with one another. They also have really big effects on things like boiling points, melting points, and things of that nature. Things with really strong intermolecular forces typically have strong boiling points, melting points. Things with weaker intermolecular forces have a lower melting and boiling point. So that sort of brought us into chapter 15, where we started really talking about solutions. And one of the important things about a solution is that the guys that have the aqueous symbol next to it is a homogeneous mixture, which means everything looks the same throughout. And there's really two parts to a solution. There's the solute, which is the smaller part of that solution. And there is a solvent, which is the larger part of that solution. And you typically mix the smaller part with the larger part, and it will all mix together, dissolve, for example, and it'll give you a solution. Once again, you take something like sodium chloride and you mix it with some water here, water being your solvent, sodium chloride being your solute. It will make a sodium chloride solution. The name of the solution is always the solute. So if you have a sodium chloride solution, the solute is sodium chloride. Most likely, if it's an ionic compound, the solvent is probably going to be water. It doesn't always have to be water as a solvent, but in a lot of cases, water is a very good solvent for things that are ionic, and things that are polar works really, really well with each other. So looking at sort of the properties of some water, our solutions, and really these intermolecular forces, brought us to this idea of why certain things are soluble or mixed with each other, and certain things are not soluble in each other or do not mix in each other. And it brings up a really interesting idea of like dissolves like, which is a common phrase that we sort of hear when we talk about solubility. And really, what it's referring to is things that have similar intermolecular forces will pretty much be soluble in each other because they're going to be able to interact the same way with each other as they're able to interact with themselves. So that's always a plus for solubility. If you got somebody that's going to interact with something else the same way it interacts with itself, it makes it really, really soluble. So when we think about things that are typically soluble, those are ionic things and polar things like a sodium chloride and water. That's going to use what is sometimes referred to as ion dipole interaction, where, for example, the water molecule, which has a positive side and a negative side, will surround each of the individual ions. So like the sodium ion positively charged would be surrounded by the negative side of water, for example, that is negatively charged, surrounded by the hydrogen side of water, which is positive side. And that's again essentially how something like sodium chloride dissolves in water. All the water molecules basically surround all the ions. Something that is polar and polar will also be pretty much soluble in each other because they would use either hydrogen bonding or a little dipole interaction is pretty much what they're going to use. And again, those are very similar types of interactions and forces, which makes those things very, very soluble in one another. Another interaction that's really soluble in each other and sometimes missed by people because we think about polar and nonpolar, but things that are nonpolar and things that are nonpolar are also going to be soluble in each other, and they're both going to use dispersion forces. So, for example, if you remember way back when you did that experiment with the halogens and the reactivity of the halogens, where you use hexane or heptane, one of those, and there was like a top layer that had a certain color and a bottom layer, and then the top layer may change colors and stuff like that. You maybe had like chlorine water or something like that, which is Cl2. And then say this was heptane. Heptane is nonpolar. Cl2 is nonpolar. That is why we expected to see like the Cl2 up there in the top layer, the Br2 in that experiment, which is also nonpolar, and the I2 up there in the top layer because both of those guys are nonpolar. That's also why in the bottom layer, which was the aqueous layer, that is where we expected to see things like, say, our sodium bromide, which is our sodium ions, and our bromide ions on the bottom there layer, which is more the water layer because it's more soluble in there. So nonpolar definitely gonna be soluble in each other, and that's because they're both using dispersion forces. That's why something like water would be a terrible solvent if you were doing something with chlorine or bromine or something like that, because it's polar and nonpolar, so they're not going to mix really well. So although water is a really good solvent for a lot of things, especially ionic polar things, anything that's nonpolar is a really crappy solvent for it. I want to say you did iodine crystals maybe the other week, and you put it into water, and then you put it into like hexane or something like that, and one it should have dissolved and one it should not have dissolved in, and then the water one it should not have dissolved. So when we talk about insoluble, really when you kind of cross over between polar and nonpolar, that again is where you're going to sort of have some trouble. If we're talking about a solid and a liquid, they will not mix, so the solid will not dissolve. We're talking about two liquids kind of being mixed together. You'll see different layers happening, right? They won't mix in that case, and they would be insoluble. So as we saw, maybe in one of those labs, miscible and immiscible are sometimes used for soluble and insoluble when you talk about liquid and liquids mixing. Miscible is when two liquids mix and it just looks like one, and immiscible is where you see different layers basically happening. We also talked about ways to classify solutions. There's unsaturated, and unsaturated basically means that you have not hit the point where the solute will stop dissolving. So in an unsaturated solution, you really haven't hit the point where you could get those guys to stop dissolving. It will continue to dissolve. So you can continue to dissolve solute in this case. And you really would be able to, in an unsaturated solution, continue to dissolve solute until you hit basically a saturated solution. And a saturated solution is the one where, based on temperature, and solubility is based off of temperature, so the solubility of things are determined by temperature. Typically, for example, the higher the temperature, the more soluble a solid is, say, in a liquid, and the lower the temperature, the less soluble a solid is, say, in a liquid. A saturated solution is the maximum amount of solute that will dissolve at a given temperature. And when you hit a saturated solution, you hit sometimes referred to as the saturation point. And that's pretty much the point where, pretty much at this point, if you made a saturated solution and you want to dissolve more solid in it, it's not going to dissolve. It's pretty much just going to kind of pile up there on the bottom, and it will not be able to dissolve anymore. Another way that we could classify a type of solution is supersaturated. And a supersaturated solution is a solution that really has, for the most part, too much solute dissolved in the solvent. As you might have saw in that demonstration, perhaps in lab, bless you. One way that you can make a supersaturated solution is you heat up a solution. And when you heat up something like water, for example, you can get a lot more solid to dissolve it in at the higher temperature. So you get all this solid to dissolve it at a really high temperature as you're heating it up. Get all this stuff to dissolve. Then typically what you do is you kill the heat after it's all dissolved, and you let this thing kind of cool back down. And as it cools back down, what's going to happen is a couple of things. It will still be a solution at this point, but because it's cooling back down, the solubility of that solvent and those solute will change as well, because it's now a much lower temperature than it was at the higher temperature. So as it starts to cool back down, solubility changes. At this point, though, it's a little too late because you've already got it dissolved. So what you really create is a supersaturated solution at that point, and it's a really sort of unstable solution. And it's so unstable, sometimes just, picking up the test tube or the flask and just, shaking a little bit or banging it a little bit, it's enough for it to realize that it has way too much dissolved in it, and all the solid will come out. Or you could actually trigger it to happen by just taking like a one little small little flake there of whatever you dissolved in it, and just kind of toss it in there. And at that point, it'll go, at this temperature, that's way too much. We shouldn't have any of this sort of dissolved in there. And what you see will go from a solution, and then all of the solid will basically come out of solution, which I think was maybe demonstrated in that one experiment the other week as well. So that's a supersaturated solution. A couple other ways we finished the first little bit of 15 about was a concentrated solution and a dilute solution. So in a concentrated solution, it's a solution that has a lot of solute dissolved in it. It's for lack of a better description, a pretty strong solution, right? So it's got a lot of solute basically dissolved in it. It is, by the way, the solute, when you talk about a solution, the stuff that's dissolved in the solution, that's really the things that react when that solution. So it's really the solute that's flowing around, that's really doing any type of reaction that may occur, for example, with that solution, is the amount of solute that you have going in there. We can make a dilute solution which is commonly what we do. We take a concentrated solution and really just dilute it down. So I think in that lecture, I used the example of like a soda with a lot of ice. It tastes really good and like a regular soda. But if you leave your cup with all the ice and it melts, all that ice is going to create a lot of water, and it's going to really dilute down your soda. And if you taste it again, it tastes a little less strong, right? It tastes more watery, and that's a more dilute type solution. Any questions on any of that stuff there that was sort of covered in that lectures? All right, so we're going to pick up here in 15 with talking about concentrations and some different concentration type of units. So the first types of concentration units we're going to really talk about here are sometimes referred to as percent concentrations. The first one is percent mass to mass. So that really is percent mass to mass is the mass of the solute over the mass of the solution times 100%. It is a percentage. In most cases, we're kind of doing a lot of times grams divided by grams here. And at the end, it will be a percentage because grams sort of cancel out when it's all said and done. Out of all the sort of percent concentrations, this is the one you usually has to be the most careful with. And you really have to be careful with the bottom part here, which is the mass of the solution. And you want to make sure that you get the mass of the solute and the mass of the solvent together when you use this formula. The reason I say you have to be careful with that is very commonly in these type of questions, they will give you that information separate from each other. So they'll give you the information for the solute, they'll give you the information for the solvent. And it's a very common error that a lot of people make is they just kind of divide by the solvent. So they see it as like the larger number. So they just take that and dissolve it. So I would say in a lot of cases, you definitely have to make sure you add those together to make sure that you are dividing by the correct amount. Now, you could definitely use this equation and we could solve for really anything in this equation. We could solve for the percent mass to mass. We could solve for the mass of the solute or even the mass of the solution, for example. But if you are given the percent by mass here, concentration, so if you were given something like it is 4.5% by mass here, sodium chloride solution, a lot of times it's a really good idea to turn this into really a conversion factor and do the calculation more of a dimensional analysis way. It doesn't allows you maybe not to have to remember the formula. You just could kind of do units and getting rid of the units that you don't want and the units that you do want. So anytime you have a percentage, right, 100 is a really good number to assume. So what this would mean is in this case, we would have 4.5 grams of sodium chloride in 100 grams of solution. And you can use that really as a conversion factor. You could also flip it around the other way and say 100 grams of solution contains 4.5 grams of sodium chloride. So that's a really good way to work some of these problems sometimes, especially if you're given the mass percent, because you can essentially just do it as a dimensional analysis. You don't have to worry about rearranging the equation. And frankly, you probably don't even have to worry about remembering the equation. Again, just getting rid of those units that you want to get rid of and keep the ones that you don't want to get rid of. Another important sort of couple of concentration units are percent volume to volume, which is what V to V is. So this is volume to volume percent. And this is the volume of solute divided by the volume of solution times 100%. And that is like, percent alcohol by volume. That's sort of what that sort of is used for sometimes. As bottom one is percent mass to volume. And that is the mass of the solute divided by the volume of the solution times 100%. I would say, unlike the first one here, these two, you probably don't have to worry too much about the bottom part there. I would say probably in most problems, you'll be given sort of the volume of the solution. You don't have to be as careful as say the first one we were talking about here. Usually what we're talking about here in terms of units is a lot of times milliliters and milliliters. This is almost like density, grams and milliliters, basically, right? And those are typically the units that we use here. So using sort of our same example there, if we had a 4.5% volume to volume sodium chloride solution, that would mean you had 4.5 milliliters of sodium chloride. in 100 milliliters of solution. Or again, you could flip it around and use it in the opposite way. Also, if you had 4.5% mass to volume, sodium chloride, you would do the same thing. You got 4.5 grams of sodium chloride in 100 milliliters of solution, or in 100 milliliters of solution, you would have 4.50 grams of sodium chloride. So again, these are ways that you could kind of turn these percent compositions into usable conversion factors, and it's a good way to do it. Obviously, just like the other one, you could also just plug and chug into the equation as well, and it should come out mathematically obviously the same as if you sort of set it up dimensional analysis in terms of the math part of it. So these are three sort of common percent concentrations: percent mass to mass, percent volume to volume, and percent mass to volume. Any questions on any of those there? All right, so why don't we try one here and sort of see. A solution is prepared by mixing 2.5 grams of calcium chloride and 50 grams of water. Calculate the mass percent here of our calcium chloride. So we're looking for what is the mass to mass percent here. Okay, so let's take a look at it. So obviously we're using our percent mass to mass here. That's our mass of our solute divided by the mass of the solution times 100%. In this case, it is the calcium chloride here. That's our solute. It is the smaller part of the solution. The 50 grams there of water is going to be our solvent in this case. So we do have the mass of the solute, which is our 2.5 grams. We have the mass of the solvent, which is 50 grams. Remember that we do need to add those together to get the correct number there for our solution, which would be 52.5 grams. And that again is what we want to use there, along with our 2.5 up there on top. So now that we have everything we need, a little percent mass to mass, 2.5 grams divided by 52.5 grams times 100%. Really, again, here the grams cancel out, leaves us really just with a percentage, and that percentage is 4.76. And you can leave it as percent m/m. You could also put in there a little calcium chloride type of solution. Any questions on that one there? So again, really important. A lot of people in this situation will divide by just the 50 and stuff like that. So make sure that you get both of those guys together. Any questions on that one? All right, let's take a look at another one here. Concentrated hydrochloric acid contains 37.2% by mass HCl. What is the mass of HCl? This contained in 35. Okay, let's take a look. Once again, here we're obviously dealing with our percent mass to mass, which is going to be our mass of our solute divided by our mass of our solution times 100% in this particular case. Here, if we look, we are given the percent mass to mass here, which is 37.2%. So we do have this guy. By the way, I knew this here was the solution, even though it didn't say it. And that's because we are looking for the mass of the HCl. And as I mentioned earlier, the name of the solution is the solute. So if you're looking for the mass of the HCl in an HCl solution, that would have to be your solute that you're looking for, which means our 35.5 grams there would be our mass of our solution. So again, that's how you can kind of tell sometimes in these type of problems. So our mass of our solution was 35.5 grams, which means we have this. You could, again, just plop it in there and rearrange. I'm going to do more of a dimensional analysis approach. So I'm going to turn this into a usable conversion factors, where that would mean I have 37.2 grams of HCl in 100 grams of solution. Or again, you can use it in the opposite sort of direction with 100 grams of solution, 37.2 grams of HCl. So with that being said, I already know my grams of solution here, 35.5 grams of solution. Once again, without maybe even knowing the equation or formula, I could just do my units to get rid of, and I could use my conversion factor here on the left and go 37.2 grams of HCl is 100 grams of solution. That's going to cancel out my grams of solution and give me 13.2 grams of HCl is basically in there. Now, if you did want to plug it into the formula, you would essentially be doing the same math. This would be 37.2% equals our mass of HCl divided by 35.5 grams times 100%. You would divide the 100 and multiply the 35.5, which is essentially the same math as you did up there, and you will have obviously the same answer in this case. So again, one of the benefits perhaps of doing it the dimensional analysis way is you don't have to worry about rearranging it wrong or anything like that. Hopefully, you could just kind of do a unit, getting rid of units type of approach. Any questions on that there? All right. So now that we talked about some of these percent concentration units, let's talk about really the most common unit of concentration, and that is molarity. And molarity is abbreviated with a capital M, and it does stand for the moles of solute over liters of solution. It is really a formula, almost like density. Just like in density, we could solve for really any of the three things in that formula. Very, very common in chemistry. We use molarity, and we can solve for all three of those things. So molarity here is moles per liter, which means if you want liters, that is moles divided by the molarity. And if you want moles, that is liters times molarity. One of the most important things when you are doing calculations with molarity that I would highly, one more time, maybe highly recommend, which is if you had a solution like 4.5 M, which is molar sodium chloride, and you're going to use it in a calculation, I would definitely take more of a dimensional analysis approach. And one of the first things you should always do is get rid of this big M, and just really get rid of the big M, and you should replace it with both units. The number always is with the moles part. So this would be 4.5 moles per liter of sodium chloride. The reason I highly recommend that you do it this way is I can't tell you how many papers I've seen over the years where people have no clue there's even liters involved or where the volume is. All they think about is M and moles and have no both of the units, conversion factor. So if you needed to, you could also just flip it around the other way and put liters on top and the moles on the bottom. So you could really use it like a conversion factor. You definitely should get rid of the big M so you can see both of those units. This also is a really important thing, which is whenever you're doing this calculation, which is a very common calculation we do in chemistry, and you're using molarity and volume, the volume should always be in liters because that will actually give you moles. And probably most of the time that you're doing that calculation, you want moles. Now, if you just take, for example, milliliters and times it by molarity, you can do that, but you will not get moles. You will get what is known as millimoles, which is like 1,000-fold different from what you're looking for. So you're looking for moles, you'll be at millimoles, you'll be off by like a factor of 1,000, which wouldn't be good. So you should always, if it is molarity by itself, you should always make sure that your volume is in liters, because that will usually 99% of the time or even more put you in the correct units that you need for your calculation that you're doing. That's also why milliliters is not necessarily bad in a sense, because molarity can also be known as millimoles divided by milliliters. And the reason for that is the milli on top and the milli on the bottom, they cancel. And now you have molarity, which is moles per liter. So it's not necessarily wrong to multiply milliliters by molarity. The only problem is most people don't realize that they do not get moles when they do that, but they actually get millimoles, which means, again, you're going to be off by that factor of 1,000. So always just make sure it's in liters, and you'll probably be in good shape in any calculation that you do. Any questions on that there? So again, very common in chemistry. All three of these gets used. So we solve for any of these three things very commonly. I would say solving for moles is a really common one, and getting liters is also very common. And molarity, when you do something like titrations, is also very, very common. So very commonly, all three sort of things in here get solved for. When we talk about a molar solution, like a 1 molar solution, what that really means, if we do have 1 molar of a sodium chloride solution, it means we have 1 mole of sodium chloride dissolved in enough water, for example, to make 1 liter of solution. I would say most of the time we look at molarity, and especially when we're dealing with ionic compounds, most of the time we do sort of keep the ionic compound together, and we look at sort of the molarity of the whole thing together. But because it really is an ionic compound, for example, when you have something like sodium chloride, and as we know, that is a strong electrolyte, which means essentially what you have in that solution are really ions that are floating around. And sometimes when we're dealing with molarity, we're sometimes interested, especially with ionic compounds, maybe what the concentration of the ions are that are floating around in the solution, not necessarily the whole thing together as a whole unit. And there is a relationship between sort of the whole thing and the ions that are present. So if we had that sodium chloride solution, and it did have a concentration of 1 molar, when it is in solution, as I just put you in that picture, we basically would have a sodium ion and a chloride ion basically breaking apart. And the way that molarity works in terms of ions to ionic compounds, the whole unit, you basically could kind of treat it like stoichiometry. So for example, when we look at sodium chloride, it is a 1-to-1 relationship between the whole thing and a sodium ion that you get. So what you would do with the concentration is take 1 times 1 molar, and the concentration of the sodium ions that are floating around in that solution that I drew to the right would be 1 molar of sodium ions. You could also do the same thing for our chloride. For every one of those, we actually do get one of those chlorides, which means we could take 1 times 1 molar. And if you were interested in what the concentration of the chloride ions were in that solution, it would also be 1 molar. Molarity is not additive, so clearly 1 and 1 doesn't equal 1. But again here, that's basically the concentration of each of those guys as you got floating around. In this case, we basically have equal concentrations because it breaks apart into a 1-to-1 relationship. Now, let's say maybe it doesn't break apart into a 1-to-1 relationship. Let's say maybe we had something like barium bromide in this case. So if we were to take our same sort of guy here and dump some barium bromide in there, we would get a barium ion, and we would get a couple of bromide ions floating around in this case. And again, if this was 1 molar and we were interested in what the concentration of the barium ions are, it is a 1-to-1 relationship, which means we would take 1 times our 1 molar, and that would give us 2 molar as our barium ion concentrations in this solution. No, we would get 1 molar if I did my multiplication right. That's much better there. 1 times 1 is still 1, I think. There we go. That's why you should pick up the calculator sometimes. All right, 1 molar here. All right, but when we look at our barium bromide to our bromide ions, it is a 1-to-2 relationship in this case. So we'd actually multiply the concentration by 2. And for the bromide here, we would get 2 molar bromide. It is basically twice as concentrated in bromide as it is barium in this case. And that's what we see in my picture, right? I got twice as much BRs as I do barium floating around. So it's twice as concentrated in here. That is the short calculation of if you are interested in what the concentration of just the ion is in a ionic compound, you basically just multiply it. Basically what we're doing here when we multiply by 1 or 2, we'll take the barium bromide as an example. So if we took our 1 molar barium bromide, that would mean we have 1 mole per liter of the entire thing. And really what we would do at this point is just a basic mole to mole relationship, 1 mole to 1 mole, just like in stoichiometry. And we would do 1 mole, the whole thing gives us 1 mole of the barium ions. Moles of the whole thing cancel, gives us 1 mole per liter of barium ions, which is our 1 molar barium ions. If we did it for our bromide, starting with the concentration of the whole thing here, it is a 1-to-2 relationship, mole to mole relationship. So 1 mole of the whole thing here gives us 2 moles of the bromide. Moles of the whole thing cancel, gives us 2 moles per liter of our bromide, which is basically our 2 molar bromide. So that's the long version of what we just did. That is why we multiplied by 1 in the first one, and we multiplied by 2 in the second one. So we want kind of the shortcut calculation of that. You just multiply it by its coefficient of how many it breaks apart into, and that will give you your concentration of just the ions. Any questions on that? So this would be only in a situation if you were not interested in say ionic compound together, but we're interested in one ion or the other or both of the ions that might be floating in the solution. Any questions on that there? So let's try one here. Calculate the molarity of a solution that's prepared by 15.6 grams of solid KBr and enough water to make a 1.25 liter solution. Potassium is 3910 there on the periodic table, and Br is 7990. All right, take a few moments, see what you come up with here. Okay, so let's take a look. We clearly are looking for molarity, which is moles per liter. I see our volume here is in liters, so we don't have to do any conversion. I will say that very common molarity questions, that milliliters to liters conversion is used a lot. We don't necessarily need to do it here, but a reminder, right? 1,000 milliliters equals 1 liter. And again, that's something that's used a lot with molarity. But since we're already in liters, we're good on that. This is our mass of KBr, which is our solute in this case. We do need to convert it into grams, our grams to moles using the molar mass, which is also a very common sort of thing that you need to do. In this case here, we basically just need to add those together and we will end up with 119 grams per mole as our molar mass from the periodic table. We'll use that to convert our grams into moles. So 15.6 grams of KBr. We're going to divide by 119 grams per mole. Going to give us 0.131 moles. At this point here, we now have the top thing that we need there for our molarity. And all that's left really is just to divide the two numbers that we need. And if we do that here, our molarity will be 0.131 moles over 1.25 liters, going to get us here 0.105. Units do not cancel, so it'll be moles stays with the number per liter of KBR, or at this point, you can go back to the big M KBR if you like. Whichever way you want to kind of do that there at the end. Any questions on that calculation there? So basically, if we weighed out 15.6 grams of KBR, dissolved in enough water to make a 1.25 liter solution, mix it up really well, we would have 1.25 liters of a solution that has a molarity of 0.105 gram, 0.105 molar, actually. Any questions on that? All right, let's try another one here. How many grams of sodium nitrate is needed to make a 2.5 liter solution that is 0.15 molar? Sodium is 22.99. Okay, so let's take a look. Obviously, we're dealing with molarity, which is moles per liter. We do have the molarity given to us, 0.15 molar sodium nitrate. We do have that. We obviously have our liters given to us. So if you aren't really sure where to go, mole seems like a pretty good move. That's good because that will give us moles, which we can then obviously get to grams by using the molar mass from the periodic table to do so. Again, here are volumes in liters, which it needs to be. I am again going to do this more of a dimensional analysis approach, just to make sure I don't forget anything. So this here means I have 0.15 moles of sodium nitrate per liter. Or again, we could use it in the opposite way. And because I do have liters, one of the nice things again about doing it this way is I don't really have to worry about the formula because I just need to cancel out the units. I need to get rid of liters. So that clearly tells me that's the one I should use. And because I know how to do dimensional analysis here, I know that basically what's on top gets multiplied and what on the bottom gets divided. So I'm going to multiply, which is the correct rearranging of that formula without, again, having to necessarily rearrange it. That is going to get us here 2.5 times 0.150. We'll have 0.375 moles of sodium nitrate. Once again, we're close to what we want, but we do want grams. So that's going to require us to come up here and do a little molar mass. So we got 22.99 for our sodium. We have 1401 for our nitrogen. And we got 3 oxygens at 16 in this case. That's going to give us 85 grams per mole. And that is what we're going to use as a conversion factor here to figure out how many grams. Once again, just doing a dimensional analysis approach. Moles has to go on the bottom so that they cancel. That leaves grams up on top. Moles will cancel, and we will end up with 31.9, it looks like. Go up here. 31.9 grams of sodium nitrate. Any questions on that calculation? So again, that number represents really if we were going to make the solution, that's how many grams we would need to weigh out. So we'd weigh out 31.9 grams of it. We would dissolve, in this case, water would be a good solvent. This is ionic. And we would get enough water to make 2.5 liters of solution, mix it up really good, and we should end up with a solution that has that molarity at that point. Any questions on that there? Okay. All right, so why don't we do this one here? In this case, we're actually looking for each of these solutions separately. What is the concentrations of all the ions? So what are the concentrations of all the ions? So for this guy, we're looking for what is the sodium and sulfate concentrations. And for this separate one, the potassium and the chromate concentrations. So again, two separate ones for concentrations. What we were talking about earlier, we have sodium sulfate here. So really the first thing you want to kind of think about is how it's going to break apart. In solution, it will break apart into a couple of sodium ions and a sulfate ion. And again, here, if we were interested in just the ion concentrations, this guy's starting at 1.2 molar. It is a 1 to 2 relationship here between the whole thing and the sodium, which means how that affects concentration is we're just going to multiply the concentration by 2, which would give us 2.4 molar for our sodium ion concentration. Once again, here, if we look at the whole thing to the sulfate, it is a 1-to-1 relationship, which means we will multiply the concentration by 1, which basically means it stays the same. And we would have 1.2 molar for our sulfate in this case. Any question on that one there? Again, in this case, we get kind of a 2-for-1 for our sodium. So we have twice the concentration of sodium than we do sulfate in this particular case. We look at the next one, which is potassium chromate. It's going to break apart kind of similar here. We're going to get actually 2 potassiums and 1 chromate. And once again, we could apply the same sort of approach. It is a 1-to-2 relationship. So we'll multiply our 0.75 by 2, which gives us 1.5 molar for our potassium. It is a 1-to-1 relationship between the whole thing and the chromate. So we'll multiply our concentration by 1, or really just keep it the same, 0.75 molar for our chromate in this case. Any questions on either of those there? All right, let's take a look then at an example where we might have to do this. So let's take a look at this one here, which is how many moles of calcium ions and chloride ions are present in 42 milliliters of a 0.35 molar calcium chloride solution? So take a few moments. We're looking for the moles of each of those ions that would be in this solution, basically floating around. Moles per liter. We do have the molarity given to us. We do not have the liters, but we do have the milliliters. So we do definitely need to convert it into liters here. And that's going to allow us really to sort of figure out our moles in this case, as that's the only thing that's happening. You can actually approach this one of 2 ways, but first I'm going to really kind of get my milliliters into liters here. So I'm going to take my 42 milliliters. Again, 1,000 milliliters equals 1 liter. That will give us 0.042 liters. So I got that in the right unit at least. So one approach would be just to get the concentration of each ion to begin with and just do the calculation for each one separately. So if we did that approach here, we have calcium chloride, which would break apart into a calcium ion and 2 chloride ions. And once again, if this whole thing is 0.35 molar, it's a 1-to-1 relationship between these guys. And that will get us a concentration for our calcium, basically the same thing here. It'd be 0.350 moles per liter calcium ions. If we do it for the chloride, it's a 1-to-2 relationship, which means we need to multiply, bless you, the molarity here by 2. And if we do that there, we're going to get a 0.7, I believe. And that's going to give us 0.7 moles per liter of our chloride. So in this case, I just got really the individual concentrations of each ion. And now I could just rearrange my equation here really and take my moles is equal to liters times molarity. Again, I can get moles, but again, you would get millimoles, which would be 1,000. So again, really important that it is in liters. So I'm just going to take still a dimensional analysis approach. So if I want my moles of calcium, I'm going to take my volume in liters, and I'm just going to use it like it is. It's actually in the right orientation there to do a little dimensional analysis. Liters will cancel, and that's going to get us here 0.042 times 0.35, 0.147. I will then just do my second calculation here for my chloride using the volume. And again, the concentration of the chloride ions that we got, which in this case, 0.7 moles per liter of chloride. Going to get us 0.0294. Question first off on that approach. The other approach would be just to do it based off of the whole concentration of everybody together. So for example, you could just do the 0.042 liters. You could times it by the molarity of the entire thing, which is 0.35 moles of the entire thing here per liter. Those guys will cancel, and that's going to give us our 0.042 times our 0.35, 0.0147 moles of the entire thing. Now you could just do a mole to mole relationship. It's a 1-to-1 relationship between those two guys. And you'll just do your 1 mole of calcium to your 1 mole of the whole thing. They will cancel, and that will give you your 0.0147 moles of calcium, which obviously, as you can see, is the exact same thing that we got this way. The bottom one would be the same calculation, except that this guy here would be the mole-to-mole relationship, which is 2 moles of chloride, 1 mole of the whole thing, and that will end you up back there as well. So if you want to take that approach where you have it all together and then just go from moles of the whole thing to moles of each ion. Obviously, as well, you want to get us to grams of each of these guys. Any questions on that there? Question on molarity, how to calculate it. All right, next we're going to talk about is dilution. And as I mentioned before, a lot of times we do get in labs solutions that are really concentrated, and we really don't want to use it for a variety of reasons, including the main reason, which is it's pretty strong and concentrated. So a lot of times we don't want to use something that strong or don't need to use something that strong. So we do a process known as dilution. And really, when you do a dilution, really the only thing that you add is more solvents. And in a lot of cases, people will tell you, hey, all you do is add water. A reminder that water may not always be the solvent, but in a lot of cases it is. So people sometimes just talk about dilutions with just water being involved. Because of that, what's happening in terms of our molarity dilution, you are really only changing the solvent part, which means that you're really only changing the volume there on the bottom, which means the bottom number gets larger, and that means the molarity goes down, right? Because you're going to be dividing by a larger number. So when you add volume or you add solutions to solutions, you're pretty much always doing a dilution, which, as you can see from this really simple little example here, molarity will constantly change. So whenever you add solutions together, the molarity of that solution will change because the volume is changing. The one thing that doesn't change is actually the top part. We didn't do anything with the solute. So the moles of the solute that you had at the beginning of the dilution will still be the moles that you have at the end. And that is what that basically says. The moles of your solute before the dilution and after dilution will be the same. As you'll learn, that's really uh, not change as you're adding the volume, while the molarity will sort of consistently change. This is one way that you could do a dilution. That is our friend, the volumetric flask, also known as expensive because it's volumetric, has one marking, which is the volume of it. Typically, when we use volumetric glassware, that's like 2 decimal places usually. So we put a little bit of water, take our more concentrated solution, add it to it, top it off with some more water to the line, give it a mix and mix, and we'll have a dilute solution. By the way, when you use a volumetric flask, what happens if you overshoot the line? Can you just pour it out? You cannot, right? Because your solute's already dissolved in it, right? So if you pour out over the line, you just poured out your solute, which means your molarity will not be the same. Perhaps that happened to some of you the other week. You went maybe over the line if you made a solution. So you don't ever want to pour it out once things are dissolved. So there is an equation for this, and I use it most of the time. Most people use this equation because molarity is the most common unit of concentration, which is M1V1 equals M2V2. And this is usually sometimes referred to as the dilution equation. This is like before the dilution. That is the molarity and volume before you dilute it. This is after you dilute it. Now, earlier we talked about if you do a calculation with molarity and volume, you should always make sure that the volume's in liters. The one exception is in this equation. You can leave it in milliliters on both sides, and it will work out okay if you want to. So if you solve for M2, it would be M1V1 over V2, molarity on top, milliliters on top, milliliters on the bottom, cancels out, left with molarity. But this equation, if you want to leave it in milliliters, it will work out okay. And that then you're dividing by milliliters, so the 2 millis cancel each other out, and you're back to moles per liter, and it all works out okay. If you want to convert it to liters on both sides, you can. Or if you're solving for a volume, you convert it to liters. You would just have liters as your volume when you solve for it. A lot of books and people nowadays use the classic C1V1 equals C2V2. C is just a generic term for concentration, because technically speaking, when you go into this equation, you can use any type of concentration you like percent mass to mass on both sides, percent volume to volume, you can use any of those type of guys. But most of the time we deal with molarity, and that's oftentimes the one that we use the most. And most people will use that M1V1 equals M2V2. Again, all the ones are typically the more concentrated stuff. All the twos are typically the more dilute stuff. It really doesn't matter as long as you keep the numbers that go together. Any questions on that there? All right, I think we'll lay it up there.